four-fold symmetry along one OO. This is what we expect. And what you can do now, you can just assign, because we know the selection rules for diamond structure. The only, as I mentioned, we don't have a 2 OO reflection, so we only have 4 OO reflections for kinematic conditions for very thin crystal. And this is what we have. So this is the 4 OO reflection, this is the 2 OO reflection. You can even calculate, let's say, the length of this vector, because I mean, for OO, this is just the square of these indices, or the sum of these indices to the square. So this is just 4 times 1, sorry. I'll just show the relation. So what you have, I mean, you have a relation between your length of your G vector and which goes 1 over the lattice spacing for these Miller indices, and on the other hand, what you have as well is the sum of the Miller indices. So if you invert that, you will see that if you divide your, I mean your real space, lattice spacing by the square of the sum of the Miller indices, and this is simply, oh no, so sorry, this is A. This is A, I'm mistaken. So this is the lattice constant. Sorry. This is the lattice constant. Now we are correct. So this is our lattice constant. If you divide that by the, by this explanation, then you derive your real space lattice, like the lattice spacing for this particular set of lattice planes, and G, or the length of G, the absolute value of G, is just 1 over E. And from that, I mean, if you want to measure lattice spacing from diffraction pattern, you would just have to measure this distance here. You need to know the Miller indices, and then you can directly measure this lattice spacing. In the first step, you would have to calibrate the reciprocal space. You would have to calibrate your camera length, because that might be off, because if you just slightly defocus, or you slightly change your turns of the lenses, then the scaling changes. As the scaling might change, you have to calibrate that using a random crystal. I will tell you use silicon, because silicon, like we know, and it's like a highly perfect crystal available. And then you can measure these distances. In this particular case, we know these directions here. We know our lattice planes which correspond to these reflections, and now we can directly show the real space crystal, how the electron will propagate through this crystal to generate this reflection. And this is the relative orientation for these 2 to O type reflections which we observe. We have these 2 to O type lattice planes. 2 to O means that our reciprocal lattice vector, due to this construction of the reciprocal lattice, just points parallel to a 2 to O direction of our cubic lattice, of our cubic unit cell. The same holds in this particular case for the 4 OO reflections. So this is like it points along the 1 OO direction of our unit cell. And now we know that this reflection occurs from a diffraction of these lattice planes. And by that, if we know the material, I mean we know what we have to expect in diffraction. If we don't know the material we want, I mean if you don't know the material, you would rather start with chemical analysis or so before you do some diffraction experiment to get into the details. But let's assume that you don't know the crystal structure of your material. This is a common question. What you would use, we would call diffraction pattern, like in a highly symmetrical direction. And you would see that on your viewing screen, you can easily identify highly symmetrical directions. And then, for a very complicated crystalline structure, you would start with some simulation to compare to your diffraction pattern. I mean, for the silicon here, we know the selection rules, just you can write them down on a sheet of paper within half a page, and you can calculate that. So we know which reflections should show up. And if you take from this direction, let's say this is along one of these edges of the crystal, let's say if you tilt to illuminate the crystal along the diagonal, for instance, the diffraction pattern would look different, because you have to keep in mind that these vectors here, they have to be perpendicular to our incoming vector. We don't give our incoming k vector, meaning that if the incoming k vector is already 1, 1, 1, so that we illuminate along the diagonal, then I mean there could hardly be an 004 reflection. Why? Because I mean the scalar product of 1, 1, 1, this is our propagation direction, and any 004 type reflection would not equal 0, so those vectors are not like perpendicular, meaning that this reflection doesn't show up in the diffraction. It could be a 2 to 0, meaning the 2 minus 2 0, because let's say we illuminate along 1, 1, 1, and we have another vector perpendicular, which is 0 minus 2, 2, then the scalar product would equal 0, meaning that along other directions you always have to think about the scalar product of your potential g vectors and your incoming k vector, and so you can easily calculate which reflections should show up in which. As I mentioned, there is software available to calculate all that, and I would like to show you very few examples using the GEM software package, which is one of the commercial software packages, which Balaji already mentioned. I mean, I have this software installed because you can do like many different calculations very easily, but there are other tools available as well. This is licensed software by Kirsch Stadelmann from Switzerland, and yeah, I mean you can do many things with that, because I mean you can do almost any kinds of calculation that you need. You can do like simulations or modeling of diffraction patterns, not only using parallel illumination, because so far we only use parallel illumination to end up with sharply focused spots with a spot pattern. We can do convergent beam electron diffraction pattern modeling with this software. You can do atomic and even not only kinematical diffraction but also dynamic diffraction. This is only kinematical so far, which is a simple approximation. You can do atomistic simulations like high-resolution TM calculations, high-resolution stem calculations, and all that with one software package. And you can use almost any kind of crystal structure, so you can utilize a crystal like a pillar to build crystal structures and to import all those files. Because I mean, the sum of this numerical approaches to one diffraction patterns, they just rely on a certain distribution of patterns and of scatterers in space, and you might be able to use extended crystals like a nanoparticle to calculate diffraction patterns, for instance. So when did we actually start? It was like 11:30. And let's just start with the next part for a couple of minutes. This is like, so this was a diffraction experiment of a semi-crystalline material. But in principle, you would like to define the region of interest on your sample. Even for such a semi-crystalline diffraction pattern, you will come and use selected area aperture to define that region to a certain size of like a few hundred nanometers or 1 micrometer. Because if you don't cut this beam, which might be pretty broad, because you want to achieve a parallel illumination, then you might, get some broadening because the crystal might bend, things like that. So We commonly use the selected area aperture. In particular, if you have a complex device or structure, and you want to select a small area, a small niche of interest, you would like to use an aperture. Those apertures, or projected aperture, can be as small as it is up to 200 nanometers in diameter. This is the first image plane, and Balaji already explained intensively that we don't use this right at the sample here to define this area, but we use a much larger aperture in the first image plane, which is back projected. And so by that, if you record this diffraction pattern, it will only generate a diffraction pattern of this selected area. This perfectly holds for when this is positioned in this first image plane, which is a little bit further below our sample. And now we have to think about what we would see if you have a polycrystalline material. I mean, for a single crystalline material, this is pretty clear, because just defining this area would lead to almost or very similar diffraction. But if you have just, assuming that you have like a polycrystalline material, which is like a coarse grain, with like several grains, I mean, you would see some more reflections. And the finer this grain structure is, or this, let's say the smaller the grains, or the larger the aperture is, the more grains in different orientations contribute to the diffraction pattern, meaning that rings, this is a little bit different to like a, I mean, this is like bi-diffraction using Israeli. This is exactly the same. And now it depends on whether or not you have the same crystal structure in there, or different crystal structures for a composite. If you have the same crystal structure, I mean, those reflections here are highly related to those rings. If you have many more crystal structures, I mean, you would observe the superposition of those contributions of the different phases. So this is what I mentioned. If you have, let's say, all those reflections are on rings, according to our selection rules, according to our reciprocal lattice, which is related to the crystal structure. And here's just an example how this evolves if you use a smaller and smaller aperture for the same grain size. So this is just getting gold film. In this particular case, you observe individual reflections due to these different grains. As I mentioned, this is just a superposition of all the contributions of the individual grains. The more of these crystallites contribute to the diffraction pattern, the more, the closer those reflections get until we end up in a homogeneous ring. And there are different ways. For instance, I had to deal with a very thin layer, which was only 50 nanometers, and I wanted to do some static area diffraction. And what I did, because this aperture is too large, I just used an astigmatic beam, which was pretty narrow, and I aligned it parallel to my cross-sectional sample to this layer. I recorded the diffraction pattern of that area. Unfortunately, I didn't take many of these, so I ended up with a really poor diffraction, ring diffraction. But what I did is, I measured at one side, I measured at another side, I measured at 50 sides, and then I simply summed up all the diffraction patterns. And so you can even go down to lower scales with sharp rings by just using, let's say, a slightly astigmatic beam. I mean, we could focus the beam by estimate, like, I mean, if you focus the beam in one direction, at least you will end up with a certain convergence angle. And as you will see, the convergence angle will typically need to broaden. But by that, I could do like a structure analysis of a pretty thin layer, let's say 50 nanometers, which was fine grained, just by averaging or integrating and superposing many of such poor diffraction patterns to come up with such a diffraction. Because I mean, for the structure analysis, it's always better to have such a defined where you can clearly observe the rings, because otherwise, if there's a slight misalignment, like astigmatism in the diffraction pattern, and those rings are slightly distorted, you would hardly realize that if you only have some spots on these rings, like in, and this is just a diffraction pattern of polycrystalline gold, like this Tibetan film, how it looks like. this is a diffraction pattern, the static area diffraction pattern of single crystalline gold. This is along this particular case 100. So this is FCC. In this particular case, we already have the 200 reflection, the key 200 reflections, and so on. And what we see is, or what we will see is that these diffraction angles directly correspond to the diffraction angles which we observe here. Because I mean it's the same material. Why should there be other reflections? So the 200, this is this ring here, it's the same distance at the same camera length. The innermost ring, this is the 111 ring of reflections, which is also allowed. It's just odd in the indices. And the next one here is the 220 ring. So it's exactly the same. This is just one crystalline, these are many crystallines. And this is what I mentioned before. You always have, if you want to do some quantitative analysis, if you don't know the crystal structure, if you want to come from here to identify, to compare with some simulation, what you always have to think about is the scaling of your diffraction pattern, which means the camera length of your microscope, which can be easy to change. There's a lot to change to zoom in and out the diffraction pattern, and you need to know your camera length. And to come up with some quantitative data, if you don't know the structure, you will always have to measure your camera length precisely, so you have to calibrate that by the use of either like such a cold crystalline gold film, because here you can just measure one gold distances of gold, for instance, to calibrate. Unfortunately, there are some reciprocal stain mass visible, we also enter in the images here, to measure those reciprocal distances to come up with a quantitative analysis. In particular, if you want to measure strain, I mean strain means small changes of the lattice constant. Small changes of the lattice constant lead to small changes of our ring diameters, or of our positions of our individual reflections. And if you want to measure them very precisely, because I mean you are below 1%, below 1.1%, then you have to calibrate them very precisely. But by that, by knowing the camera length, you can always measure, because you should know your wavelength, you can always measure like your green space spacings. So, and with that I would like to close for today. And let's have lunch, so we have to finish the diffraction part with some examples of selected area diffraction and convergent electron diffraction early morning tomorrow. And unfortunately our intention was to finish even the diffraction contrast part by today, because there will be the first TM demonstration this afternoon, but due to lack of time or too much information provided by me, we're going to cover that tomorrow. And with that I would like to thank you for your attention and see you later. This is not tourism.
Then what remains is objective schema. For that, I think it will be better this is gold, this is different sample.
अभी एक्चुअली सर इज अलाइनिंग है ना अभी एवरीवन चेक करेंगे
तो आप रिकॉर्ड कर रहे हो
बुला लो फिर स्टूडेंट्स को कॉल कर
हाँ नहीं वेट पहले हम एक बार कर है थोड़ा ये फोर्स देखा अभी मैंने सॉफ्ट नॉर्मल फाइन ट्यून ऑब्जेक्टिव एस्टिमेशन को कैसे दिखाना है लेटेस्ट स्लाइड शो ऑन दैट right now we see some kind of one fringe, black fringe around it. So that is because हमने head height को adjust कर ली है, but it is still not like क्योंकि this is a mechanical arrangement, so it's not very accurate. So the final tuning we have to indeed do with objective focus itself. So we will try to do it, and so अभी it is showing a black fringe. Means probably that it is in meter. We'll just check. So अभी जो है वो fringe चला गया. If I go still further down, then a white fringe should come. अभी वो white fringe थोड़ा आ गया है. Now when is objective astigmatism कब आता है? If let us say more than that, I am thinking of that this is much useful. ये जो whole method है. So anyway, doesn't matter. So वो थोड़ा एक्सपोज हो गया था ज़्यादा इसलिए थोड़ा टाइम लगेगा. अभी थोड़ा मैंने intensity को कम कर दिया, then it started behaving properly. So one way to identify regarding the objective astigmatism is to look at this pole, for example. And here, if this is a Fresnel fringe, because we are away from the proper focus. Okay, that is fine, but this fringe should be uniform. If it that there is a fringe is an indication of that one is away from focus. But if that fringe is not uniform, that is an indication that there is objective astigmatism. So right now I would say it's not that bad because it is more or less uniform. थोड़ा ऐसे जरूर लगता है कि this side is more prominent than that of this. तो थोड़ा बहुत astigmatism हो भी सकता है. But by and large this is okay. And whenever we acquire the images also, that time also has to be like थोड़ा हम under focus में we acquire the images, that is they look with a better contrast than to acquire with over focus. Because with over focus they look dark, there is a dark fringe, we can check. So right now I believe that I am in the under focus, that's why I am seeing the bright fringe. And if I now go towards the right, means I am increasing the current, then first of all these white fringes should disappear eventually, and then yeah, so right now you see that the no I'm sorry, this is the intensity, yeah, that is the wrong knob. So this is the knob that we say, this is the objective. So we say that we were in under focus, that's why the bright fringe, and then now I'm going to the right, so the white fringe has gone, and we still go further, then a black fringe should appear. Indeed it is appearing. there is one grid because somebody opened the door also. So now you see there is a black thing. When it is over focus means more current. Over focus is not that good. So you will come back and let us say that the objective activity is good. There is another yeah, so like this would be a better. When there is a slight white fringe, that looks much better. So we have learned these 4-5 steps. What remains is, let us say, yeah, I think this is good time to begin. So you can call everybody. So who? No, he is my student. जो operator है, he is working with some, yeah.
So tomorrow you will be talking about indexing, no?
Yes.
So please include that portion of like carbon loss. In carbon loss, we got the amorphous sample and some of them only exhibit the pure lattice or the crystals.
Actually, there are two types of controllers, breaking and carbon controllers. Breaking component has crystallinity and other one is the condition.
So how?
Let me think. First, whatever is there in my head, let me first explain.
Okay.
I think yours is a typical, better. He has more experience. Professor Benjamin worked on graphene. He even talked about diffraction patterns from graphene. So I have never worked on carbon materials. So you should.
So maybe after lecture I should.
Yes, he will be here in our institute for 2 days. So 2 days means not so many. He also wants to make some revision, but he is the right person.
What is the material?
Okay, so substantial. So most of us are here, isn't it? Okay. So I was saying that you will first look at the microscope, learn about the microscope's components, etc. And in the first part, I am going to explain the TEM microscopy, diffraction contrast microscopy. The second part, which is scanning transmission electron microscopy, that will be covered by Professor Benjamin. He is very good in scanning transmission electron microscopy, so I will leave it to him. Now explaining about the machine, so it will be more or less continuation of my lecture, so whatever that 30-minute talk that I gave. So you see, if we look from the top, that top part which you see is the whole thing is gun. Yeah? And if you see on the front, that there in the corner there is a huge tank, that big tank, that is a high tension tank it is called. That is an accelerator that generates high voltage. So our machine is working with 200 kilovolts. So that 200 kilovolts is generated there and then it is supplied to the gun. Okay, so that is the gun part. Then we have, okay, so afterwards this one is the, okay, so from up to here is somewhat the gun, from here to here is the condenser aperture system. Condenser system or illumination system. It is called system because it has got at least 2 condenser lenses and then a condenser aperture. So this one is the condenser aperture. Okay, so after that comes the main part of the microscope. It is the objective lens, and this objective lens is very important because it forms the first image and the first diffraction pattern, and the quality of the microscope is very heavily dependent upon the quality of the objective lens. Now also that is an area which has got most of the very important components that are in that very thin, or not thin, but in this much of a portion, which is here. Let us say from here up to here. Actually, in this portion, so many things are there. Our sample is here. This is the holder of the sample, and this is the objective aperture. Plus, there is a detector. So this is a EDX detector, and so on. So it's in a very narrow region. So many apertures and systems are there. Okay. So after that, this is the selected area aperture. So this selected area aperture is in a plane which is called as first intermediate image plane. Okay, and so that this plane is equivalent to that of our sample. Yeah, sample plane is equivalent to that of an image plane because they are optically equivalent or optically conjugate. Now we said, yeah, and the objective lens is here. Now whenever we draw the diagram, we draw it like objective lens, and on the top is the specimen, and on the other side is the image and the back focal plane where the diffraction pattern. First the back focal plane and then the image. And here you see, I am saying this is my objective lens and my sample is actually inside. So that is only for schematic drawing, or in light microscope that holds good. But here this lens is so big. I mean, electromagnetic lenses are of this size or like that. So effectively, although we say that the lens should be above or the specimen should be below the objective lens, here in fact it is actually sitting inside. Okay, yeah, that's one thing. Second thing is, we said that between the sample and between the and the first intermediate image plane, what is there between the between the lens and between the first intermediate image plane, or even between the sample and between the first intermediate image plane, what should be there? We discussed. Huh? I mean back focal plane. Yes, correct. Back focal plane should be there, in which the diffraction pattern should happen. Suppose this is lens, this is parallel light which is coming, then that lens will make a point at the diffraction pattern. The parallel rays will be focused at the back focal plane, and that back focal plane is actually the where our objective aperture is there. Okay, so fine. Now we understand this geometry more or less, and then these are the intermediate lenses and projection lenses, etc. And finally the screen, on which it's a fluorescent screen. So if the electrons, they hit the fluorescent screen, they fluoresce, and so we get the image. Alternative way is that one can take out this, one can take this out. So if I do like this, then the whole thing comes up and the electron beam goes directly to a camera system, and that's where image is digitally recorded. Or you can also catch it here on the screen. So yeah, so these are the nanoparticles that we are seeing, and these are gold nanoparticles, and as you can see the scale bar is 15 nanometers, and here it must be something like maybe 20 to 25 nanometer must be typically the size of these nanoparticles. Then okay. Good. So is there any, I told about the EDX detector system also. Then apart from that, there is the anti-contamination device. So it is like a liquid nitrogen container, and this liquid nitrogen container enables this portion around the sample, this chamber around the sample to remain cold. So locally there won't be any contamination. So that improves the vacuum and is able to maintain better vacuum in the region around the sample. Alright. So apart from that, we have, here are the two detectors. This is the bright field detector, bright field STEM detector, scanning transmission electron microscopy detector, and this is the dark field scanning transmission electron microscopy detector. So about these, how it is inserted, etc. I will let Professor Benjamin do it. This one is the bright field scanning transmission electron microscopy detector. By that I mean bright field means it's like almost yeah, and this is the dark field. But this dark field, depending upon which sector is used or what camera length is used, it can be also called as HAADF detector.
Combination of both these two is header.
No. High angle annular dark field. So it's this is a dark field detector, and if you operate it at high angle, can be called as high angle annular dark field. I think it is same. Yeah. That's why I said depending on which mode you drive, it may be having sectors and so on. I don't know also the details, but now we will talk about the alignment in the second part. But have we discussed all that we wanted to learn? I believe yes. Correct. So is there any question at the moment to you? Yes, that is true.
इसमें भी दो होंगे, दो इसमें तीन होंगे.
Yes. We have to remove the fluorescent screen. We have to also block it so that the outside light doesn't interfere, etc. So this is so-called lead glass, which can withstand vacuum, because the whole column inside is under vacuum. Correct? Is under vacuum, so it has to withstand vacuum, and secondly, it should also withstand any X-rays if generated inside the chamber. Those X-rays should be absorbed by the lead glass. That's why this glass is called, or is made of, I mean it's lead glass. I don't know exactly what its composition is, but its function is that it will not let X-rays to come out, because if they come out, then they will affect us. So that's one thing. Regarding looking at the sample holder, etc., maybe little later, either when we change the sample or if we don't change the sample. When okay, Benjamin, yes. So
Sorry for the
no problem. So what I decided was I began with the normal TM part.
Yeah, sure.
And the sample is still the gold nanoparticles, but we didn't change it, and it's
your idea was to start with
aluminium.
the same part of the aluminum, or you didn't exchange it?
The gold nanoparticles were inserted right from the beginning, because we thought for aligning the microscope it would be better. So, and we stayed with that, and I would say that let's stick to this for the time being. If needed, we will change the sample. There is also some discussion regarding stem alignment. Geol local representative engineer has come, and he somehow was saying that the detectors are little misplaced or whatever. So
Yeah, but that is no big deal.
Oh yeah.
I told him last time that it's displaced.
No, but this one is a different person. 2-3 days back.
But he also realized that it's displaced.
Yes, he also
Okay.
realized. But maybe you can little bit explain. So for the stem part, we are going to rely directly on him. And good. So what I have done is I have explained the components of the instrument. Okay. So great. Now second step is that we are going to we are going to see how to align the microscope. These few steps that I discussed. But before that, again, whenever you have a question, I think you should just feel free to ask. And in a way, I mean, these gold nanoparticles, they are not ideal for explaining, let us say, the diffraction contrast microscopy. But let us still stick to it for the time being. And if there is an opportunity, and after the STEM, if we still have time, and we can. And if we have also time, let us say, you also have time, we will insert the aluminium sample and try to study its microstructure as I explained. But even if that doesn't materialize, most of the things you would have got, so that's not a problem. Now, so since we are not asking any questions at the moment, I would. Yes.
Can we tilt our sample?
Yes. Now, this particular detector is only is a single tilt detector. Single tilt holder, not detector, single tilt holder. which means that it's almost like this hand is my detector holder, for example, and the sample is somewhere here. Yeah, the sample size is 3 millimeter. In this case, these were gold nanoparticles. They were deposited on a copper grade, 10 grade, and that 10 grade of 3 millimeter diameter is sitting somewhere here. It's like this. Now, single tilt holder means the only tilt that is possible is like this. Whole thing moves. Yeah? Had it been a double tilt holder, they would have made an additional movement mechanism wherein this part will be able to move like this also. But that is not available in this particular holder. The double tilt holders are more expensive. So for routine work, we don't use that unless it is necessary. Okay. Now, okay, how to tilt? That's also an important thing. Now, one way of doing it is that they have kept some pedals here. So you can see, I have in my hand, these are the pedals. So it is possible to there's one more for the beta tilt, but in this case, there's only one tilt. So had it been a double tilt holder, there would have been one more connection, and that connection would have gone here. So here it is written tilt Y. This is tilt X is automatically there. There is a motor which moves the complete goniometer. This whole part is called goniometer. So the whole goniometer moves. But right now, okay, and I believe that this right hand pedal is exactly the one which is exactly the one. You want to switch on the light? Is the one which is, but let us check. So what we will do is, we will keep looking at this at this point here. So you see here TX, yeah. So I will try to tilt it, and let us see if that value changes, and some of you can maybe try to see if one can feel whether this is rotating or not. So let us see. Nothing is happening. Okay, let us try with the other one. Yeah, so with this I think it is changing, yeah. And could we also see if this was moving? Yeah, so this is the way in which the sample tilt happens. That's what, I mean, you will learn eventually about diffraction patterns, zone axis, and like that, and there how to tilt from one zone axis to another zone axis. So this is how it is done. And I mean, you see if we have a silicon single crystal, and then it has the FCC structure, and if you let the electron beam fall from along 100, and now you want to change it to 110. So how to change that? These are the this is how you do it as far as mechanically. But you still need to orient it. I mean, just tilting in one direction wouldn't, you may end up anywhere, isn't it? So for that, you also need to look at the Kikuchi pattern. So that's how you get a inclination. But that you will learn more about it, and that's why for that, those kind of things, either aluminum sample or even better, the silicon crystal sample would have been much better. But let's take it the way it comes. So tilting is explained. Anything else? Okay. So now some of the steps that we need to regarding the sorry I should be now some of the steps. So right now you see here the magnification is 150K. Yeah? That's little too much, so we will reduce it, and so I have reduced it to 100K. We can even go to maybe 60K. Yeah? And I will still maybe just that one can see it better. Therefore, we will take it on the camera. Let us see. So, and now it is very heavy exposure. Therefore, it is saying beam too high. So I am making the beam. I am spreading out the beam so that the intensity decreases. And I will try to do as much alignment as is possible on the screen so that everybody can see this, because here it is not possible for everybody to see. So
for spreading the beam, you have to adjust the numerical version.
Yes. So this one is brightness, not exactly numerical aperture, I would say. So this is the brightness knob, and this brightness knob is directly connected to the condenser lens system, which is here. So what I do is, if I change the focus of the condenser lens or the excitation of the condenser lens, either I can make my beam to converge. If I make the condenser lens very strong, then it will converge the beam. If it converges, then the most of the intensity is concentrated in a less amount of area, so the intensity of the beam will increase. If I do the other way around, that is, then it goes in the, then it becomes more broad, but the intensity decreases. So here, that's what we have done. Now, okay, so we are seeing these nanoparticles. Let these be our regions of interest, or we will use them to do the alignment and so on. So what we said, we learned first that we will make our objective lens as standard, so that we start from some level to align the microscope. So I press this button. This is, I mean, it's nothing. It's not. It shouldn't be called as a step, but just that it's so important.
How do you decide the value of the operating voltage actually? You have started on 60 K, but you have
No.
That is
This is magnification.
Okay.
This is magnification.
So that is the voltage is around
Voltage is 200 kV.
200.
200
I thought you have reduced to 60 K.
No. 60K is magnification. Because we said that the first few initial steps can be done at low magnification. So we'll do. In this microscope it is probably 80, but I know that 120, probably 120, yeah.
So limit of the magnification for this 10 limit?
It depends from STEM mode or TEM mode, but with TEM one can easily go up to 1100 and even maybe little
So
higher
the
than
point
that.
resolution should be around 1.7 angstrom roughly. So every magnification above, you want to, I mean, as a pixel size, and your sampling of one atomic column, you need 3, 4, 5 pixels, and it doesn't make sense to go even further because you don't gain any more information. You don't, enhance resolution by going even further up. I suppose the maximum value is above, you know what you need for atomic resolution imaging, but then you just limit your field of view. So.
Okay. Then the second step we said is aligning the condenser aperture. So that is little difficult to show on the TV, on the CCD screen, but this is such a there's nothing finer detail to be seen. So you can all see also from where you are. So what I am going to do is I have, let us say, focus the B. Yeah. So it is
the
now.
same knob as brightness or like
Yeah, same
That
knob.
is the same
Yes,
knob.
same knob.
Condenser.
Right now we are playing only with the condenser.
Condenser lens too.
Yes.
That
So-
converges the beam.
Yes.
Condenser lens too.
I'm not sure if it is.
This one, the condenser,
Ah,
the
the
sampling.
condenser.
Yeah, no. The question in a way is important in the sense that there are two lenses, and also even Professor Benjamin also explained to you that the condenser lens system consists of condenser lens 1, then 2, and this is out. Now here there are two. One is the spot size, and the other is this knob. So here also you will see here there is one more button which is called spot size. So one of these is to condenser lens 1, and the other is to the other one. Which one is that I at the moment do not know. So now, okay, so this we have focused, and now from the focus, so when it is focused, it is slightly off the center. The center is a black hole which you from there cannot see, but since I can see, I will just now I will shift the beam. Yeah? This beam shifting is a very rudimentary operation which anybody, and that we have to do many times. For that, this is the shift, and this is shift X, and this is shift Y. So with that, I will just shift it so that it comes to the black part. Now you see there is some black, one tiny hole inside. I can see it there, very small
Can I go
hole.
closer?
Yeah, you can. Okay, so it was only 2-3 millimeters away. I centered it. Fine. And this step one has to do so many times during one's working that it is not considered as a bit.
So basically the center of the column, like alignment.
No, yeah, I mean
Black part.
beam we are centering it. Yeah, in a way it is optic axis,
Optic
and let us
axis,
assume it's the optic axis. This black hole is supposed to be the optic axis. And if the beam has slightly shifted, then you put it to the shift it back to the center. Now, now we said our aim is to do the second step, which is the centering of the condenser aperture. I am now in the focused state of the condenser lens. I go to, let's say, over focus, and now it has symmetrically opened, but that was because the condenser aperture was very well aligned. Let us therefore, by ourselves, just to practice, let us misalign it. Okay, so what I will do, I will maybe change it like this and this one like this, and let us see what happens. So you see, it has more or less completely gone. So I think that was too much. Let us reduce the magnification. So I hope that the beam etc. is still there. So and
So you upper one, sir, you have just up.
no, it is still there.
Yes, just up upper one, sir.
Yeah, this is the upper one. I just checked if this
Okay,
was
right.
inside or whatever, so I just want to be sure. So let us try to get it. Yeah, so now you see it is there, but if I had done it little more, one shouldn't do it too much also, I think. So anyway, I stay like this, okay? And now we see how it behaves. So I have now centered it, yeah? And you see this was indeed too much that I had done, yeah? So when I now come to focus, you see it is going in. So now, if I succeed in centering it, then we should say that we have learnt it very well how to center, because it is quite significantly misaligned. That's what I realized. Okay, so good. Yeah, let me still bring it little bit to the. So this is, let us say, our focus position, and if I go to over focus, it is coming to this side. If I focus it and if I go to the other side, it's going to the other side. So this is what we want to correct. So I will, yeah, so now it is off that, so I will bring it in the center. Something like this. But remember, see, right now it is away. There is also a very normal tendency. I think, oh, beam spot has gone to the other side. I will bring it with this. This will not help. So if the condenser aperture is, if the beam spot has gone away because the condenser aperture is misaligned, then bringing it back with beam shift will be not a correct way of doing things. Okay. So
then sir, how will identify?
how will you identify? Yeah, it's a good question. See, do like this. Focus it. We focused it. When we focus it, it is at the center. Only when it is out of when it is spread, only then it is going away. This is an indication that that is the problem.
And when we will see,
If the aperture is off from the optical axis, then you select electrons passing through the condenser, which are off the optical axis. Meaning, if you focus the beam now, because they pass under a certain angle through the sample. If you focus, they might be centered. But if you spread the beam, the spread will move, because this is the tilt in principle, because your aperture is off. You shouldn't apply beam tilt now, although we have beam tilt available, because there are things that interplay, and you have to separate those. And if you go through a good training at the microscope, you should be able. There are manuals available how to do this stepwise, and those in principle. You have two options. Either you just simply follow what you do, or you somehow understand to a certain extent what you do. But in principle, because you can compensate for beam tilt, so you might be able to compensate for such a movement, but this would not be correct. It's not only a movement. If you look at the spot, there's also some intensity asymmetry.
Yes.
So which is severe.
Yeah.
And so this is also another indication for a misaligned aperture. So, I would say with some expertise and experience at the microscope, you get into those details.
Now you see here, it appears as if the intensity is more to the left, to the deep corner, and it's not at the center. And so on. So
this is because you have the intensity gradient in your condenser system from the optical axis to these outer regions. And if you select, some with a shifting aperture, some intensity, you anyhow end up with a certain.
when we will use this beam tilt
For dark field imaging, for instance, in principle the beam should not be tilted. But if you want to do, Balaji is going to tell you about tomorrow.
Yeah.
If you want to do dark field imaging to select a diffracted beam for optimal imaging, you want to shift the beam in the diffraction plane back to the optical axis. But how can you shift the diffraction pattern? You shift the diffraction pattern by tilting the beam, by keeping the sample constant. And you have to realign the sample as well to keep the excitation conditions. But I'm just going to tell you what tomorrow.
So then we keep doing. So one has to repeatedly do it, and then at some point of time the iteration or repetition is no more essential. So I have centered it and then I focus it. Yeah, so far it's fine. I go to the other side. It looks more or less fine, but I can give one more try. So, and whenever you correct it, see, I am in the, let us say in the which focus is that, maybe under focus, and I see I need to correct it. You don't correct it fully, you correct it only 90%, because you never know when you go from under focus to over focus, how is that going to be. So that's the trick. So yeah, now I have, and now I come to focus, yeah, and then I see that the beam has little bit, even when I am focused, it has gone little bit off, but let's not worry too much about it. I mean, we also want to proceed, and then I over focus it, and then it's more or less fine. So I would say that condenser aperture is now centered. Okay, so that step we have done, and so we have done the 3 steps which needed to be done at low magnification, and now we go to the 4th step, which is centering of the objective lens, and that we do by so-called high tension centering or high voltage centering,
So there is no automated alignment for particular voltage level? Because I heard
It might be that that there is
different voltages.
it is, they are there. So when you do the alignment, there must be some provision wherein you can save all the parameters into a file. That must be there. But I am not so much aware of it. How to load the
newer
file.
microscopes.
Yep.
I mean, if you have like an older microscope from the
Yeah.
1980s, I mean, at Erlangen we had 2 CM microscopes, Philips CM. There is hardly any chance. There's just a basic alignment and you have to do everything
Correct.
on top. So there are no user alignment files that you can save. I mean, new microscopes, they provide those capabilities where you just save your file, you know that.
Okay, so now for the other alignments, let's say the voltage, objective lens centering using maybe voltage centering. So what is done is that in voltage centering, they change the voltage that is supplied to the microscope by some amount, maybe plus minus 10 volts or whatever. I don't know exactly by how much, but they change it. Now when the voltage is changing, then the power of the objective lens changes, or effectively the focus of the objective lens changes, or effectively the magnification changes. And if the objective lens is exactly sitting on the optic axis, then only its magnification should change, but it should not shift from in the screen. The image shouldn't shift. So in order to check that, we put in one nanoparticle there, for example, and this step, for example, can be demonstrated on the screen. And for this, I go to high magnification slightly, at least 100K. So we are at 100K and maybe even a little more. And I will little bit make the intensity weak, and we go on the screen. Okay, so this is how it is, and I will. So now we see that there is some rim around it. You see, this is the hole in the carbon grid, and there is a dark fringe. This fringe is actually because we are, although we have, did we correct the Z height? I think we didn't, isn't it? So we should go back to correcting Z height. So for that maybe we will slightly, no, it's alright. Let's see how it works. Our Z height shouldn't be so off also. So I am making this image wobbler, and so see, it's moving, but our camera system is probably slow to react, or the acquisition time must have been so large that it is not able to follow the wobbling. Since I don't regularly use the microscope, so I have to see I want to change the acquisition time to little faster. Yeah. I will. Okay. I will. All right.
Just
Yeah. Yeah. Okay. Now it's much better. So you see, it's vibrating, and we try to minimize that vibration. So I have pressed this Z plus button. It's probably improving. I have a feeling. Maybe I can't be sure. So
this is another tilt in the objective lens, you know. This might be, you might introduce tilt of your electrons through the microscope by shifting apertures for sure, as well as by using, because now you have your coils to tilt, so your beam tilt coils, which might be a little bit off. So this is what you compensate for, because the propagation parallel to the optical axis is essential, because otherwise you might run into trouble with coma. Coma means this is the propagation of your beam in a tilted molecular sample, and so you would see that in a high resolution image.
okay, so let's say that we have corrected the Z height. Sorry. Okay, and then so I stop it. So we have understood how to do it, and then you realize that that fringe, which was earlier so strong, has also reduced significantly. So we have seen that, and we have done it even at higher magnification. And you see, if there is some asymmetry in this fringe, that if this is not homogeneous, the Fresnel fringe, that is an indication that there is objective astigmatism in it. So, I mean, that the fringe is there is an indication that there is some defocus. But that there is inhomogeneity in the fringe, that is an indication that there is objective astigmatism. And that can be also corrected by, so we just, and now let's quickly see the effect of defocus also. So here is our objective defocus. So this is coarse, this is fine, and let me see how, so we have done the Z height to the degree possible, and the fine tuning can also be done using this objective focus. For example, I am going in over focus, and then you see that the dark fringe has appeared. If I go back to close to focus, this fringe disappears. So this would be more or less the proper focus condition, but you see the contrast is slightly better. If I go to slight over focus, when a faint bright fringe appears. So this would be something, because there is a faint bright fringe, and that gives a better contrast to the eyes. So we have seen, and I would, since I more or less think that this is a uniformly bright fringe, so I say that the objective astigmatism is not there, so we don't have to correct it. Had it been there, one way in which it could have been corrected is, we go to this diff steg, and here I see that there is objective stigmata. I press this button, and then using these these bottom knobs, one could try to make that fringe uniform or homogeneous. Okay, so we are
going to talk about the Fourier transform to show that, to correct for the astigmatism, because I mean, this is a coarse alignment of objective astigmatism.
Correct, yes.
For atomic resolution imaging, we would calculate in live view the Fourier transform of the atomic resolution image, and we will come to the transfer function next week, how an atomic resolution image forms, and in the Fourier transform of the recorded image, you see far better the twofold astigmatism to correct for the just with these fringes. I mean, there should be a
there is already, so I don't know if it is possible to choose a window or like that, but I see here already a T, so maybe we can just
yeah. Oh yeah. So there is our image, it's amorphous, and this is the Fourier transform of this amorphous image. In principle, it should be, for an optimal system, it should be some white spectrum here, because all the frequencies in space contribute to such an amorphous material. But what you see is some rings here around. And this means this is the Fourier space, meaning that large object details here show up with very close to the central point here. And large frequencies resemble very small object details here, okay? There is a certain limitation of the resolution, of the point resolution for such a microscope. And here now you see that all the frequencies in this image, this is like just Fourier, how is it called, like this, like a superposition of many sine and cosine functions for the different directions to build up this amorphous picture. For crystalline materials, you would only observe several frequencies in the picture because you have your, like your periodic.
Only definite lattice
yeah, because
spacing.
you have your, exactly, because you have definite lattice spacings. And yeah, I mean, we are going to address that next week.
Yeah.
In the
But-
crystal structure, we will get the very pattern view, like something is.
No, you take any crystalline material, it has some lattice constant,
Yeah.
and it has got 100, 110. These are the only lattice planes that exist. So, but in the amorphous material, there is no such thing. There is a periodicity continuous. I mean, there is no any periodicity. All kinds of, either you say no periodicity or you say that all periodicity.
One second. So just
Okay.
Hallo.
Ja,
Ah ja.
ja.
Ah, das ist cool.
Es ist noch nicht so klein genug.
Ich guck mal ganz kurz die Kamera.
Yeah, we should speak in English, otherwise they will record the German. That's also not too bad, I would say. We will record in German.
This is the thing. Integration. It was an integration.
Can you call Manu or Ajay? Yes. Yeah. Yeah. Speed up is hellbound. Nicht.
Aber das ist integriert, also wir tun das immer.
We want to do FFT, live FFT.
Just to see the light.
Actually, in this camera, there is a problem. Only one thing can run. Either you will see FFT or.
That's good.
Okay.
In Qatar, you can simultaneously.
This is AMD.
Okay, then let's just demonstrate
Yeah.
that. I mean, if you use the Fourier transform, which is just calculated from all the recorded images, what you see is, so this is the recorded image, and it's just integrated. Don't mind about that. We were just told that you cannot record both simultaneously or calculate that simultaneously. And what happens here, now the Fourier transform directly shows you the contrast transfer function, or the square of this contrast transfer function, which we are going to explain next week. This transfer function just explains how good specific frequencies from the real space are transferred into our image, so from our exit wave function below the sample into our image. And in that Fourier transform, you directly see astigmatism. So it's far easier than just using, I mean, the fringes are for coarse alignment. Now it starts the FFT. And you might just distune or misalign.
Yeah.
What's the magnification? 200,000. Where are the particles that are? This is the particles. Let's try to. This is. This was the magnification you worked at, right?
I think so.
What was the high magnification?
Maybe 120.
I could actually know when you don't see it.
Yeah. Strange.
You know what I mean?
Even this one is not showing properly.
I can ask the service.
Yeah. Shall we abort it once and then we will
Yeah,
try?
I already tried. Yeah, I avoided it already. I gotta ask him.
He will explain little later when he is anyway doing high resolution TM. So anyway, we have seen one way of getting a rough estimate about astigmatism in objective lens. So we have seen it from the homogeneity of the Fresnel fringes. So now, so the alignment is now so far fine, and we now try to let's say, so we'll now try to
Click the light.
okay, so there's
Yeah, this is in the Microsoft, so it was good. But nonetheless, there's no, it doesn't change if you go quickly, it changes. No, it's not changing.
I don't know. Yeah. Now it's good. So this is how one would see this FFT Fourier transform, and if these FFT rings, if they are not circular, then one would understand that there is astigmatism in it. And then again, by the same steps as we did earlier, just as we tried to make that Fresnel fringe homogeneous, we try to make the FFT rings also circular, and that's how one does the correction. Okay, so that's, I think, so far fine. And at the moment they look to be fairly circular, so I would assume that that there is not significant of objective astigmatism.
logic,
Yes.
would you just detune it to,
All right.
because now we see that the amorphous material in the back,
Yeah.
and if you detune it, let's say drastically, you will see the impact on this like image of the amorphous support field.
It's now gone.
Yeah, because we came closer to focus. So now you see again, you will see rings are coming. Yeah. So
this is defocus, so the structures get broader in this, let's call it high resolution image. If you change defocus,
yeah. More away from focus.
doesn't matter. No?
Yeah,
Get
so
closer, and then
Now we come closer to focus.
this is far, so the structures are coarse, and if you get closer and closer to focus, the structures get finer, and the rings disappear in the Fourier transform. You see that? And if you go from under to over focus, those rings will come up again.
Again, they are out.
But this means that there is also some contrast inversion in the atomic resolution image, as we will see next week. So from bright atoms to dark atoms, there is some dependency on the defocus all the time. A strong dependency on the
Deliberately spoiling it, let's say. So I go to objective stick and
It depends on the defocus for such a microscope. There are different defocus values which are optimal. One is the best point resolution, which is Schatzer defocus. There's another one which gives you the least contrast, this is called Gaussian defocus, this is 0. And there are different values how to generate contrast. Some are very well defined because you know this defocus value, you can calculate that for the experiment voltage. There are many, if you are just in between, then you get a high resolution pattern, but it's not best defined. So the best resolution is only given for accepting one defocus value.
means effective. Then like polycrystalline material is there, polycrystalline gold film is there. So I just take it focus and I take it effective of that. So it will come like subclubbing or
Yeah, it's one defocus value. You can say that you are like in focus, you have to find that focus, and as you can see, you just rotate the knob, you will end up in over or under focus or something like least look.
I made it deliberately stigmatic, so I can
May I
now.
suggest you go even further, just a little bit, and just remember your rotation direction to see the image, what changes in the image.
Yeah. So
Then
now
now,
it is in this direction.
you see already some streaking,
Under focus.
or even further. I mean, this is not bad.
yeah. So now I think we already can see.
It should be streaking from the lower left to the upper right. So put HRTM lecture. But this is what you can use to optimize for objective estimates. Because the low magnification includes the repeatability.
So I am correcting it again, and it becomes more circular, more or less. Okay, so somewhat.
So every time we have to do this exercise.
I mean, if you are doing high resolution, then one has to be more careful. But for routine diffraction contrast imaging, as I said, and that too, you only usually end up checking. Most of the time, it's okay. So, okay, so we have known the alignment, and now I will. Okay, so let's. We'll identify some of the sample now, which is nanoparticles in this case, and we'll just acquire. We will see if there is an area where there are so many nanoparticles, numerous nanoparticles. It will be possible for us to get a diffraction pattern, and let's try to acquire one, or at least try to identify. So.
for live
This one? So you see here I see a little bit more of these nanoparticles, but even these I think they would not suffice. They should have been slightly little more, would have been better. I don't think this will give us a ring
So you
pattern.
mean you can use the largest aperture. You don't care about the amorphous substrate and, you know?
Yeah, but I think right now there is no selected area aperture at the moment.
Yeah, but no means it's a large one. I mean,
Yeah,
you don't need
okay.
perfect rings just to
Correct.
demonstrate. you
Okay,
know.
all right. So
There should
so-
be some.
okay. So now we try to make a diffraction pattern from this, or indeed let's have the largest one just to let them show. Okay. So this is the object selected area aperture, and you see that this selected area aperture is inside the first intermediate image plane, and that's why when I put it like an image, I see it. Otherwise, I shouldn't have seen it, but I see it because it's in the same plane as the sample. So I'm seeing it. I can even center it. It's very easy to center, and okay. So I try to bring as many nanoparticles as is possible. I think this is the best that can be done. So, and let's now try to, let me just test it here because diffraction pattern is very intense. Therefore, one should.
I wouldn't show it on the
Yeah, that's
camera
what.
because you have very small number of
Correct,
particles. So
correct. That's.
You know, the direct beam is very intense
Yes,
and the
yes.
scattered contributions
What?
are pretty.
Yeah, it's I think some again defocus I believe. So let's see. Yeah. So it was this they were slightly defocused. So now they have overfocused. Okay. So since our diffraction pattern from such a sample which is very dispersed, very few nanoparticles, is going to be such that the zeroth beam is going to be very strong. If I directly capture it on the CCD may get damaged. So I will first try it on this one, select area diffraction, and I see some.
Oh, are you searching for the beam stop?
Yeah, I got it. And I still take it to the maximum. Yeah, so I have, and I will try to acquire it. Let's see. Okay, so it's slightly displaced. I don't know the reason why that I should have, I could, but then it will be a little difficult. The spot has been blocked, and these are the rings that we are seeing. Okay, so that's let's say ring pattern from nanoparticles. All right. So I will then get back. And
Would you mind to change the camera length so that we see a little more?
Okay. Yeah. So.
And is it a square CCD camera or if this is rectangular image? Can you enlarge that view? Because it was
At the corner.
lower edge.
Yeah, because I think the diffraction pattern got shifted. This is my feeling. I mean, shifted means I should probably check it. So.
Diffraction mode, to change the camera length, you use the same knob which is called the magnification, like an image. It's the same, it just switches from the image mode to the, let's call it magnification and diffraction mode. So it's just the same twin knob, so there's nothing special about it.
So shifting the diffraction pattern would be with PLA, is it?
Is it not the deflection coils?
I think it's PLA. So
Yeah. Just try.
It should be. And then it should be shift or it should be this one.
Did you change the camera?
I did it.
Yeah, because it was pretty small camera.
Okay, so let's go to higher. So this is
Yeah.
3.4.
Further, it's just.
I think that's where what is this one,
Oh, yeah.
0.3 meters now. Usually we work with
Yeah, it's
0.2.
this way.
Yeah, yes.
No, I mean just for the demonstration, go up to
Okay.
like 1 meter, like 1 meter or something. Even further. So now,
Okay.
just refocus and then it should be okay.
But I don't see the rings because they will become too dim.
Oh, you can see them on the camera. Yeah,
Beam
yeah,
stop.
this is the beam stop. Yeah, this is the beam stop.
Yeah, the
No way, you don't see anything.
the camera is poor. It has very low dynamical range.
Yeah,
Okay.
but I don't know what. Do you think it's too low number of particles? Or?
No, yeah, that's one thing. But
Yeah, but we should
What we are trying actually changing the camera lens, then what is the effect of the
yeah, the diffraction pattern should become bigger when we use a bigger camera lens. So that's what.
यहाँ पर जो डिफ्रैक्शन जो लिख के आ रहा है दैट इज द कैमरा लेंस DIF
Which one? This one is the
कैमरा लेंस
camera lens. Yeah, and it should change here also, but I think it just didn't. So maybe.
Sir, camera lens is too wide.
Yeah, now. Alright, good. So I now want to show some bright field image, and then we are more or less done, I would say. So we click on. So after I show maybe one just bright field image, you want to show high.
Those particles get darker that diffract into those angles, and the other ones which don't diffract, they appear bright as they did before. But the other ones that strongly diffract, they even get darker, by that he enhances contrast. This is how bright field imaging with diffraction contrast works.
So these are the images as they look like now with objective aperture in, and I will just take out. Maybe I don't think it will hamper too much with the CCD camera. So you see, we do see some contrast here, and let us see how it looks like if I remove the objective aperture. So I mean, I don't think it was so visible, but that's also probably because I don't know why it didn't show much. No, that I pulled out.
I mean, what you see here, for instance, just in this particular case, you see this white or this brighter area here. This is some delocalized and diffracted intensity that comes from this particle here. And now we are slightly out of focus. This is why we have this delocalization of image information. So this bright area or this intensity here belongs to that particle, and it's shifted in this direction because it is diffracted into that direction. If you now focus, just focus a little better, this will merge. So this is the direction of diffraction, And if you introduce, okay, no focus. Yeah, this is close to somehow close to focus. And if you insert the aperture again, it should almost fit the same position. Now you stop, it's okay. Even with the larger one. Now it's gone. It's totally gone because you block off this diffracted beam, meaning this diffracted image intensity. So if you have always these delocalization effects, you know, if you have, let's say, particles with different sizes, you always have a defocus issue because you cannot focus all at once. If you insert an aperture, you block off all these diffracted contributions, so you can minimize these, let's call it delocalization effects, or these diffracted contributions. You know? So it's not only about enhancing contrast, but it's also about like yeah, I mean it's not a matter of focusing, but it's, you know, for such magnification it would definitely be better. So I mean, to present such an image, I would always prefer to introduce an aperture because the image quality is far easier to interpret.
Yeah.
So this is standard wide field imaging, just by inserting the aperture.
Okay. So now I will attempt to get high resolution. Let us see. So I take out the objective aperture and yeah. So and we go high with magnification. We try to play with focus a little bit. Yeah. So.
But you're far from focus. You're from
Yeah.
fringes. So.
Yes.
And
there's astigmatism, which you see now here. The fringe is
Gone.
far smaller than here, or
Okay.
far thinner. So I suppose that there is like some.
that point.
It automatically zooms in for
Yeah,
the FFT.
yeah.
You see. Okay. I mean, you can.
Randomly try with stigmator correction.
Not randomly, but you can just optimize the basis like of your fringe. Not like direction of your crystal, and then you observe the lattice planes where the G vector is perpendicular. So the contributions that you get in the diffraction pattern, these are the lattice planes of the same crystallite that you should see in your atomic resolution image. Because I mean, this is what happens. I mean, you just select another plane, diffraction plane, image plane. And for atomic resolution, it's just that you increase the magnification. So between bright field imaging with an aperture, and you take the aperture out, and then you go up in magnification. There's no difference. There's no specific mode. Meaning that it's the same lattice planes. And you use the diffraction mode to align the sample, to align the crystallite, to tilt it into zone axis. Then you switch to image mode, and you go up in magnification to record the high resolution image. There might be some fine tuning because between image and diffraction mode there might be a slight misalignment of the whole system. So meaning that finally you align the image mode to improve even like this, or to enhance the accuracy of this alignment. And this is, for instance, a disadvantage of such kind of microscope without an aberration corrector, is this delocalization effects. So you saw this diffracted intensity with this brighter shadow or this ghost image that was shifted. And this is what you always have because, I mean, you don't have the best resolution at zero defocus where they match, but you go to under focus and you always have the shadow images of these diffracted contributions slightly shifted. So the boundary of the particle under those conditions is not clearly defined, not on the atomic scale. With an aberration corrector, your particle is atomically sharp, so the intensity appears in the image where it originates from, the same atomic column or the intensity. So this is an advantage of an aberration corrector. So if you work at interfaces, and you are interested in like an atomically sharp interface, there is hardly any chance to get a really good insight with such kind of microscope. So this is, it's not only the resolution of these aberration corrected microscopes, but it's the sharpness of your object details in an atomic resolution image. So this is another big advantage, because you always have here, if you defocus, depending on the defocus value, always this, let's call it ghost images of these diffracted beams, slightly shifted in the respective directions, depending on your defocus. The further you defocus, the more they move into that direction. This is like, let's say, one of the disadvantages, or one of the advantages of aberration correction. One of these. But for 200 kV, I mean, those particles are already 30 nanometers, and gold is pretty heavy, so it's already getting thick. It's not too thick, but and of course, in those particles, for instance, what we have many defects, as you can see. I mean, there are twins, there might be dislocations, there is strain involved because you see intensity variations. So it's unlikely that the whole particle can be perfectly aligned in some excess condition or so. I mean, to tilt one particle, if you start tilting, it will move. And then you have to shift it back mechanically using, the stage. And then you have to tilt it further. And during that whole process, to align it in one specific orientation, you would have to observe the diffraction pattern all the time. So you have to switch between the diffraction mode to observe the diffraction pattern, then you tilt further to observe the diffraction pattern. And this is how you align such a particle. This is how you align every crystalline material. But for, let's say, a single crystal or a cross crystalline material, this is pretty easy, because, I mean, every slight move doesn't have such a severe impact on the diffraction pattern. If you move here and it's out of your selected area aperture by 100 nanometers, then you don't observe the diffraction pattern anymore of this specific particle. Or if you condense the beam slightly, just to focus the beam on the particle to observe the diffraction pattern, then the particle easily moves out of your illuminated area. And so this is an iterative procedure, and it might cost you like 10 minutes just to align one particle if you are really interested in one specific particle. Or if you have like a fine-grained material.
But is it the only advantage of safe corrector?
No, the tilting.
Safe corrector actually, why is it because one of the would be told?
No, one is a better resolution. One is let's say this delocalization effects, although this is still astigmatism, I would say, but this delocalization of these ghost images. The third one is that you know your CS value. The CS value is small, and you can use the spherical aberration correction for very specific imaging conditions. In this particular case, commonly the atomic columns appear dark in Schatzerte focus. So the atom columns are not bright. Intuitively, you would expect that atoms appear bright, but this depends on the defocus. And with an aberration corrector, you can work, for instance, under negative CS conditions, so you can set a negative value of your CS, you can overcompensate for CS. And if you go to a very slight overfocus of a few nanometers, then your atomic columns are bright, your boundaries are atomically sharp, and your resolution is at 50 picometers instead of like 180 picometers. That's very clear. So we have, in principle, 3 advantages of aberration correction. Not, now we have 2 aberration correctors. In principle, you might have one in the imaging system. This aberration corrector in the imaging system compensates for this here, so for high resolution TM imaging. If you put the same aberration corrector in the illuminating system, I mean, you want, for stain imaging, you want to form a fine electron probe, but the side of let's say the convergence angle of the probe is limited for atomic resolution imaging, meaning that the current within the probe is limited. And for atomic resolution imaging, you want to have an extremely high current in an extremely small probe. And with an aberration corrector in your imaging system, you get an even smaller probe by a factor of probably 2 or 3 or so, with a far higher current. So without aberration correction, you can hardly do atomic resolution spectroscopy, because the probe is simply too small. You will always hit adjacent atomic columns. If you go for, I mean, you can do, even without an aberration corrector, you can do atomic resolution stem imaging. I'm going to show that next week. I tried that here with the instrument using these samples, but it appears to me that there is some disturbance, so it has to be mechanically stable, because it is, so the vibrations. Although you don't see those vibrations now in the image, even at atomic resolution, it appears to be pretty stable. I mean, they're like 20 meters. No.
It's quite stable.
Yeah, but as they are touching the table, you will immediately see them in stem image. So when you direct the effects, they can tell you. And there are many more aspects. I mean, there are 20 people in here, so the temperature changes. Temperature change within the lab here plays a role. An aberration corrected instrument that immediately causes drift of the focus of your probe. If the focus drifts up or down due to temperature rise. Temperature stability is another big deal. So
he's getting it now.
No, but I mean, it's similar to, it's just
Magnification, yeah. And also higher magnification.
yeah.
Thickness is too much for
But it's far out of focus. I mean, here it was not that bad, so. And there's some astigmatism still. You see this delocalization, the fringes here in the vacuum on the, I mean, the particle appears to end here. Because this is gold, there's even some inelastic scattering, phonon, excitation things, absorption contrast, so that overlaps with the phase contrast. And this is this delocalization I was talking about, you see. In principle, the intensity shouldn't be there to interpret the data, so there are no atoms. But there is intensity in the image, like periodic intensity.
That can only be eliminated by the aberration.
And it depends on the defocus here. Change the defocus. So what I would like to show you tomorrow afternoon, we're going to have an exercise, and I would like to show you using some simulations, just in principle, how sensitive this contrast is on the local thickness of the sample, on the local tilt of the sample with respect to the electron beam. So just to demonstrate you that in principle without simulations you can hardly interpret such an image. It shows periodic contrast, but you never know in principle without knowing the exact focus value where your atomic columns are. So this is what you cannot say just by intuitive interpretation of the image. I mean, these are just rows of atoms.
Oh, the lattice.
Yeah, but this is this is only one color of a plane. But probably you shouldn't spend too much time on this right now. I mean, you already saw just, let's say, the principle.
Yes.
And I would like to show you just as like complementary technique stem imaging. And I would like to do just on the one hand side just to switch to stem mode, then to briefly align. And I would like to convince you that, I mean, if the basic alignment is pretty good, it only takes a few minutes to align stem mode. And now you see the astigmatism again. So there's the overlap of this. No, these are not the reflections, like the reflection pattern, but these are just the. No, this is not the rings are just due to the contrast transfer function of this ellipse. He's currently. Why does it actually see into the image for the FFT?
try for the stent. Moment. So, why did we do this?
I just asking. It's just a very fine.
Yes, actually, that's a step.
Sorry. Okay. Okay.
Is it due to cooling water?
Yes. The chiller has like something.
And without cooling water, it automatically turns down, isn't it? So I wanted to do some stem imaging right now, just to switch to stem imaging to show you just some, let's say, diffraction contrast in stem imaging and pure chemical contrast. And I mean, we're going to do that, I would say, this week, Monday to Wednesday. There should be an opportunity that you join the other groups in the afternoon, at least for the second half. I mean, to demonstrate that doesn't take too much time. I would just briefly go through the alignment a little bit faster. We've got pre-knowledge, I would say, and it might last, let's say, half, 45 minutes or so at the end of the demonstration. Just using this gold sample, I mean, we will not demonstrate any atomic resolution stem imaging here because with 20 people this is not reasonable. So, but just to show you that there is a certain contrast. We might think about using the aluminum foil sample because we're going to see for next time. Because I mean, I would say the polarities and suns are a little bit better for what we want to do.
Yes. Grain size.
So we're going to see. Just to show you the effects. Okay.
So we close it and tomorrow we will.
Early finish today.
So हम लोग ये कर सकते हैं जो सारे ग्रुप्स हैं ना मैक्सिमम पार्टिसिपेंट दे कैन कम हियर दे कैन डिसाइड 16 नंबर एंड वन बाय वन वी कैन कम हियर एंड not one by one means one, that is 3-4%.